Okay, so we'll welcome back. Week 3, and we are going to spend time checking the validity of, I guess, a linear regression model. And there should be an S or an A here, an S there or an A there, but whatever. Okay. Before I get started, I just want to check how's everyone doing. This week's homework was okay.
It was a little hard.
A little hard.
But it's okay.
It's okay. Which one was hard?
The prediction interval.
Prediction interval using the output from R and not the built-in functions.
Exactly.
Okay, so probably that one. Yeah, there's one where you're trying to figure out SXX, right? Sum of squares x. So if you look through the textbook, there is a relationship between S, the estimated standard error, the standard error of the slope, beta 1 hat, and the sum of squares x. So there's a relationship between those three. You have 2 of those values, so you can derive the third one. You already figured that out? Okay, so, but that was why it was hard. Okay, so, but yeah, I mean, it's homework, right? It's good. Okay, anybody else? We all good? Yes?
How do we find the mean value when we have the regression line?
How do you find the mean value when?
Like for 2.5, we have to compare the regression lines between 2 plots, where y was dependent on x1 for one plot and y was dependent on x2 for another plot.
Okay.
And
which one had better fit?
yeah, no, we were just asked a question for RSS and the RSS, right?
Yeah. So you don't need the mean value to figure that out. You should be able to just look at which model does a better job of predicting y, and that should shed light onto your answer of which one's going to have larger sum of squares due to regression and which one's going to have larger residual total sum of squares residuals, or residual sum of squares, RSS. So you shouldn't need to figure out the means to get those things. I think you can just look.
Okay.
Is that okay?
Yeah.
It's more of a conceptual thing than a calculation thing. Or that was not your question?
No, I was just kind of confused for like the sum of squares. It's based on the fact that if we didn't have a predicting value,
Right.
predicting variable, then you use the mean value.
Oh, it'd be the mean value of the y, which would just be if you look
The midpoint.
the midpoint of
Okay,
all those
cool.
data
That's
points.
what I did.
Yeah. Yeah, exactly. Okay.
Another question?
Yes.
So for the very last problem,
Yes.
it's about...
Confidence intervals and 95% of the points not being in there.
Exactly.
Yeah.
Could you briefly explain the answer?
Asking me for all the answers. Okay.
Turn it in,
Okay, so that one, yes. The confidence interval is an interval regarding the mean regression line. So the true line that exists in the population, it's a confidence interval for that. It has nothing to do with future individual data points, which is what the guy is talking about when he says 95% of the data points aren't within the confidence interval. That's because the confidence interval doesn't say anything about that. On the other hand, a 95% prediction interval should contain about 95% of the data points. With a confidence interval, you have to say I'm 95% confident that the mean regression line is in here. You cannot say there's a 95% chance that the mean regression line is in the interval because the mean regression line has no uncertainty. But with a prediction interval, you can say there's a 95% chance that the next point drawn will be inside this interval, and that's allowed. Okay. Does that answer the question, kind of?
Just want to make sure that I understand
Yeah.
a concept correctly. So the prediction interval is just, if you look at the graph, is it just a prediction interval for each value of x?
When you look at the graph, so you're graphing the prediction interval. It's this fat thing, right?
Exactly.
Yeah, that is, yeah, what it is well, you know, when you tell R to graph something, it doesn't understand functions. It just says, here's at this x value, this I'm going to go to this y value, and at this x value, I'm going to go to this y value. So you just give it a series of like x values, and you calculate the lower bound, and it's going to graph that down here, and you say, here's a series of x values, calculate the upper bound, and it calculates a series up there, and then it just shades it in.
Cool.
Yeah. Okay, so let's just recap what we've done so far. Week 1, we just reviewed inference stuff, confidence intervals and their interpretations, hypothesis tests and their interpretations. We introduced simple linear regression in week 1, but that was the bulk focus of week 2. We talked about fitting a model, doing inference, and making interpretations on those model parameters. And we also talked about the analysis of variance. Okay. So this week, we're going to spend the time going over model diagnostics. And these are tools that we can use to check to make sure that our model is valid. There's a bunch of assumptions that need to be true to make sure our model is valid. And so we have some tools. We've got leverage that helps us identify potentially troublesome points. We've got residual plots and standardized residual plots to see if there is information missing from our model. We have Cook's distance, that should actually be capitalized because it's a person's name. Cook's distance to estimate the influence of an individual point on the fitted regression line. We also have plots for checking the normality assumption of the errors, and plots for checking the assumption of constant variance. Okay. We'll also cover transformations to possibly turn an invalid model into a valid one. It's not a fail-safe method, but sometimes it does the trick. Okay. And then on Wednesday, so I'm going to have an extended dplyr tutorial. So if you are here just in my 101 class, I invite you to come to class an hour early at 3 o'clock, and I'm going to go over the package dplyr in R, which is a useful tool for manipulating and handling your data frames. You filter records out and you create new columns and things like that. It's pretty great. So come to class at 3 and we'll have an extended tutorial on dplyr. If you can't make it, I'll record it and I'll try to make sure that the sound is working, and I'll post resources as well. Okay, so we'll see how that goes. Okay. All right. The big picture, the most important lesson of the week is this. Okay. If your model is invalid, all of our inference tools, confidence intervals, prediction intervals, hypothesis tests, your p-values, all of that stuff will be invalid. Okay? If your model is invalid, everything, all of these statistical tools, it's no good. Okay? Estimates of parameters, they will have no applicable meaning. So it's absolutely critical that your model is valid before you do any kind of application with it, before you make interpretations or make decisions with it. Make sure that your model is valid. It's easy to lose sight of this because a lot of times you just take data, throw it at R. R says, all right, here you go. And you say, well, great, there we go. Maybe not so great. Maybe there's things invalid with your model, okay? And the tools that we're introducing this week exist solely for the purpose of making sure your model is valid. So this is the big picture thing, okay? Don't forget this as we go through all of, the details. Okay, and then just one thing I want to mention before I go on. So on Friday, I said you don't really need to know the derivations and math results for simple linear regression, and I still stand by that statement. And I did list off some things that I said, these are the math results you should know, right? Like this is ANOVA, sum of squares total can be split into sum of squares regression and residual sum of squares. And I listed off some of that stuff. There's one thing I should have added or had on that list, and that is our estimate of the variance sigma squared is given by this quantity. The residuals from your model, you square those and you add all of those up, and then you divide by n minus 2. And that will give you an estimate of the variance sigma squared. Okay, so I left that off. This one you should also know. Okay, so talking about checking model validity. So we go back to Anscombe's 4 data sets, and this was from week 1. And the thing was, all 4 of these have the same mean value for x, the same mean value for y. They all have the same correlation. They all have the same standard deviation of x. They all have the same standard deviation of y. They all have the same fitted line, all of that stuff. So if you throw any of these data points into R and say fit a linear model, it's going to spit back the same results for all 4 of these models. But a linear model is only valid for this one, okay? A linear model is probably valid here, but the linear model that's valid over here is not going to be the linear model that's valid here, okay? This one's a different linear model. So this one's inappropriate because it's curved and all of this. So we can kind of get a hint at this if we look at the residual plots, okay? So you have different residual plots. And for a linear model, the residual plots are going to look the same whether you plot it against x or you plot it against y, because x and y are linearly related. Okay, so when I plot it against x, so in the next slide I'm plotting the residual plot against x. Basically, just imagine the line running through here, and we're just subtracting the value of the line from each of these data points. So right here, that's what happens. Okay, so we have a line running through here, and we subtract that line from here, and it kind of shapes this. Here we got a line kind of running halfway between this data point and the rest, and so when we do our residual plot, it looks like this. Okay, so these are residual plots, and so this one we see random error, and that's a good sign. We want random error, and that indicates our model's a good fit. And all of these things, we see patterns in our residuals, and that would indicate a poor fit. Okay, or I should say it indicates that there is information missing from our model. Okay, so here's why we want no patterns in our residuals. The reason why we don't want any patterns is because when we create a regression model, we want our predictions or our fits to be as good as they can be, to be the best, meaning that we have taken into account everything that can be used to make a prediction. And therefore, after this prediction, we have no idea whether the actual value is going to be larger or smaller than our prediction. We have no idea what it should look like. When we see a pattern in our residual, that indicates that there was additional information that we could have taken into account to improve our model. Okay? And so patterns in our residuals indicate that there was something else that we could have included in our model to get an even better prediction. Okay. So that's what this slide says. All right. So here, here's a tool that we can use. So residual plots are good, and there's a tool called Leverage, and this talks about the x component of a data point, and basically it just says, is this data point close to the other values? Okay, so if you have most of your data points here and a particular value is in there, it's not going to have much leverage because it's close to the other x values. On the other hand, if you have most of your data points here and you got an x way out here, this data point is going to have lots of high leverage. Okay, and so leverage helps us identify if a particular point exerts an unusual amount of influence on the model, okay? We can kind of label these as bad and good leverage points. And we would say a leverage point is a bad leverage point if it has high leverage and is an outlier, okay? And it could be called a good leverage point if it has high leverage but is not an outlier. And these are kind of terrible definitions for what bad and good leverage is. And that's because, you know, a good leverage point, quote unquote, could actually be a misleading point. Your model might actually not be the correct model to use, but a good leverage point might mislead you into thinking that it's okay. And meanwhile, a bad leverage point may not necessarily be bad, but just an indicator that something is wrong with your model, which ultimately is a good thing because that leads to you refining your model, okay? Okay. So here I'm going to use x, which is the points -4 through 0. So -4, 3, 2, 1, 0, and then 10. So in this case, the bulk of data points goes from 0 to -4, and then this value 10 is going to be a point with high leverage. Okay, and then here for y, I'm plotting the same values. The first 4 values are going to be exactly the same, except the last one for over here is 0, and the last one over here is -11.4. Okay, and we'll fit an M good, model good, and model bad. Okay, and this is what it looks like. So model bad, we can see most of the data points are over here, and we have this point, and this is our leverage point. And this one's also a leverage point, but we can see how this kind of fit is in line with the rest of the model here, and where this one kind of doesn't fit that, okay? And so if we were to fit a regression line, this is what the regression line would look like, whereas over here, if we fit the regression line, it looks kind of like this, okay? So this would be considered a quote-unquote bad regression point, and this one would be considered a good one, okay? Okay, before we go on, I'm going to take an aside and talk about regression in matrix notation. Have you guys had linear algebra? Yeah? Okay, okay, so we're okay with matrix notation and stuff? Maybe, kind of. So, you know, our book has shied away from matrix notation, but it's coming, okay? And it's inevitable. So we're going to, I'm just going to introduce it here, and when we get to multiple regression, you would have already seen it, okay? So for simple linear regression, we've presented our model as an intercept plus a slope times x plus an error, okay? We can write this in matrix form with y and x and beta and e, and these are all matrices, okay? I don't know how to get the beta to go bold in this thing, but that's that. Okay, so you know, we can treat y as the observations of y, you know, from 1 through n, and then if beta is the slope 0 and b1, and our x matrix is going to be our x values and a column of 1s. Okay, and so that way when you do the multiplication, right, you do you go like this or whatever it is. So you'll see the 1 multiplies with the beta 0, and the x1 goes with the beta 1. Okay, and so it'll end up looking like that. And then here we're adding our residuals, or the unaccounted for error in our matrix notation. Okay, so is this expression okay? Showing that it's the same as this. Okay, so now that we have established this, okay, in matrix form, the least squares estimate of the parameters beta can be shown to be x transpose x inverse x transpose y, okay? There's a proof for this in the book, okay? So, which means that when we want to fit y to our our data, our fits for y is going to be x times this thing, beta hat. Okay? And so we have y hat is equal to x times beta hat, which is this, and so if I replace that, put this in where beta hat is, we get y hat is equal to x transpose x inverse x transpose y. Okay, you're going to see this thing show up a lot in regression. Okay, and so we have given this quantity right here. This is called H. This is known as the hat matrix because when you multiply y times the hat matrix, you get y hat. Okay, so this thing is called the hat matrix, or H, and it's x times x transpose x inverse x transpose y. It can be thought of as the projection of y onto the x space. So it's basically the projection of y into its hat form. Okay. Yeah. Okay. So anyway, you have this result. So this is the hat matrix X, H. Okay. All right. But this is where this part comes in useful, is that when we talk about the leverage of a point, okay, the leverage of a point is the leverage of point I is the ith diagonal element of the hat matrix. So it is from H sub II. So so the hat matrix, when you do all of this out, if X has 5 points in it, your hat matrix will be a 5 by 5 matrix, and if X has 50 points in it, it'll be 50 by 50. It'll be a 50 by 50 matrix. Okay, and so the leverage of a point is the ith diagonal. Okay, and there are elements that aren't along the diagonal, and you've got the ijth point. Okay, and that is, let me just make sure I get this right. It is the covariance between the ith fitted value, y hat sub I, and the jth response value divided by the variance of the jth response value. So this is what it is. So when you fill in the rest of the hat matrix, it's this. Okay. So do you need to know this? No. Okay. I don't think so. All right. It's good to know that H is called the hat matrix, but do you need? I don't know. Maybe, but probably not. Okay. But when you follow the notation in the book, I don't know, the J's kind of like pop out of nowhere, and when I was reading, I was like, what? How did this guy get here? So I just want to kind of talk about this hat matrix existing, and so when you're reading the book and you see the I's and the J's, and you're wondering where the J's are coming from, it's coming from this hat matrix IJ. Okay. All right. Is that cool? Did you guys have questions back there? You're good. Okay. All right. So as far as leverage goes, this is the stuff that I do want you to know. Okay. So the diagonal of the hat matrix is the leverage of a point. And for simple linear regression with a slope and intercept, okay, which is what we've been doing, the leverage of the point can be determined with this formula. Okay. You don't need to memorize this because, well, it's easy to memorize, and I'll show you why. Okay, we're just taking 1 over n. Okay, so every point in their leverage, so if there's 10 points, every point's minimum leverage will be 1/10. Okay, and over here, what this is just imagine calculating the variance of x. You do x minus x bar. Okay, and you add those up for all of the x values. Basically, it just says how much is this particular point I contributing to this total. Okay, can you guys see that? So it just says how much is this point contributing to this total sum of squares x. Okay, and so when you put those two together, if we add all of this up, what is it going to add up to for all n points? Well, this part is going to add up to 1. And then this part's also going to add up to 1. So everything down the hat matrix, the diagonal, if you add them all up, that all adds up to 2. Okay? And I guess what you should know is that if you have p coefficients that you're estimating, it's going to add up to p, all right? So with the hat matrix, all the elements add up to 2, and so we can think of the average leverage to be about 2 over n, okay? So, so if you think of leverage that way, I think it's kind of easy to keep track of in your head rather than memorizing all these formulas. If a point has double the average leverage, so in our case 4 over n or more, it would be considered a high leverage point, okay? All right, so we can get, so I mean, you can calculate leverage this way in R. There's also a function called influence in R, which is nice, and you just call influence and you say it returns several things, but you just say I want the hat, okay? So remember our data set, we had 6 data points, right? -4, 3, 2, 1, 0, plus 10, okay? And so here, if we do 2 over 6, we see the average would be 0.33, and so double that would be 0.66 or 0.67. And so the high leverage points would be anything over 0.67, and we see indeed these ones are not high leverage, but the last one is high leverage, okay? And both, it only depends on the x, so they have the same, whether it's the bad model or the good model, the points have the same amount of leverage from the thing. And if you calculate the hat matrix yourself with x, you know, x transpose x inverse x, whatever, and you look at the diagonal, it will match this thing, okay? All right, so again, this is what our thing looks like. And this is worth repeating, at least I wrote that on the screen here. And leverage is simply a measure of how close or far a point is from the rest of the points concerning the x variable. Good leverage could actually be misleading because the current model could be incorrect, but it doesn't seem so with the point of a good point. And bad may just be an indicator. And it's always a good idea to look into the points with high leverage. All right. And yeah, so over here, if we fit a quadratic model, it could actually accommodate this point quite well. If we fit like a parabola here, it could fit it. So maybe that's the correct model. It's hard to say when you only have one data point out here. Ideally, we would gather more data, and that will give us a better idea as to what it should look like out there.
Question?
Yes?
So is leverage a way of looking at how much a point contributes to the validity of the linear model, or
Contributes to the what?
validity?
Validity of the linear model. I wouldn't say it contributes to the validity, okay? It just contributes, it kind of how much of influence does it have on the kind of the fitting of the model, right? So, because if we think about linear regression, it tries to minimize the squares of the residuals, okay? So ones that are like way out here, they're gonna, if the model goes like this, it's going to have a large residual, and when you square it, it's going to have an even greater impact. So when a point is all the way out here by itself, it tries to accommodate this this extreme thing. Okay, so I would say that's just what leverage is. It's hard to say, you know, whether it's a valid model or not. That's really a human subjective call, kind of. And you know, if you know what we're looking at, then perhaps you can say that can't be the valid model because you have scientific knowledge on these, I don't know, physical phenomena. Okay. Here's another tool, standardized residuals. Okay. So we already talked about looking at residual plots early on with the Anscombe data set. Okay. But there is a complication with that in terms of how useful the residual plots themselves are, and it's that the variance of any particular residual is actually depends on the leverage of the point, okay? And so if a point has high leverage, the expected variance is actually going to be low, okay? So as the leverage increases, this amount is going to shrink down, okay? So if we take the square root of this thing and we throw in our estimate s instead of sigma, we essentially get the denominator here, okay? And so we're going to standardize our residuals. We're essentially turning them into z-scores. The mean of residuals is 0, right? So if we did a z-score, it would be e, the point, minus the mean divided by the standard deviation. That's essentially what we're doing here, but we're subtracting off 0, so this just remains e on the top, and we're dividing by basically the standard deviation, but we've substituted s rather than sigma. Okay, so this is called this is the standardized residual. If you look it up on Wikipedia, they call it the studentized residual. Okay, and there's the internally studentized, which is what this is, and the externally studentized, which I wouldn't worry about, but basically you calculate this thing as if you were omitting the point that you are estimating here, okay? So anyway, standardized residuals, this is what we have, okay? And so this is what our bad model looks like with a regression plot. So this is a residual plot. Okay, so we're just basically subtracting off the value of the estimated line to create our residuals, and this is what it looks like. If we used standardized residuals, so notice this data point doesn't look so extreme, right? Out here, because the regression line is trying to accommodate it, its residual doesn't look so crazy, okay? But if we standardize it, okay, we see it says, hey, this is pretty far out there, especially when you take into account that the variance of a point with high leverage is supposed to be low. Okay, it says if we're saying that the variance of a point with high leverage is supposed to be low, but it's quite high, so it pops it out there. Okay, so just looking at those two, the regular residual plot versus the standardized residual plot, we can see how the kind of the outlying unusual points kind of get emphasized a little bit more with a standardized residual plot. Okay, and the other nice thing about standardized residual plots is because now that they're essentially z-scores, we also kind of have a rule of thumb, right? With z-scores, we know if you got a z-score of more than 2, that's pretty unusual. More than 3 is really unusual, and more than 4, it's like whoa. So so we're essentially turning them into z-scores. So now now we've got a pretty good idea of how unusual a certain residual is. Okay, what did I do? Okay, and then so this is for the good model. Okay, when we look at the residuals for the good model, looking at the residuals versus standardized residuals, we don't really see a difference when the model is good. Okay, between the residuals and standardized residual plots. Okay, the scale changes, but our biggest residual is 1 unit away, or a little bit more than -1 units away over here. Okay, yeah. So now that they're standardized, z-scores less than 2 is unusual. When you have a large data set, okay, we actually kind of loosen these kind of rules up because a lot of points could get flagged as outliers, especially when you have a large data set. So we move these out to 4 and -4. And of course, like everything where you're moving boundaries out, there's a judgment call. So maybe there's a in-between data set where 3 is a better number, okay? So the identification and examination of outliers is very important to the processing of determining if a model is valid. Okay, so let's take a look at this Treasury bond data. from our textbook, okay? And so I don't know if you guys invest in investments, okay? The typical thing is you've got stocks and you've got bonds, right? So stocks go with the market and they're pretty volatile, high risk, high reward type of thing. If you want something safe, you might go with something like a Treasury bond, and at least in the United States, these are very safe purchases because you can very reliably say, I'm going to buy this bond and the US is going to pay me this amount of growth. And so the amount, there's something called the coupon rate when you buy a bond that says this is how much you're going to grow, how much it's going to grow. And so the amount that the bond sells for is going to be very much related to the coupon rate. Okay, so we're going to look at bid rate versus coupon rate. Okay, and so this is what our data looks like, and we fit a model here. Okay, and what we notice is we've got these three things. Okay, so the rest of the model, it seems very clearly, as the coupon rate goes up, the bid price goes up. Okay, and down here we've got coupon rates that are quite low, but the bid price seems unusually high. Okay, so what's going on there? When we try to fit a regression line, the blue line, we get this thing, and then when we fit this is the confidence interval for the mean regression line. It's this shaded area here. Okay, and here is the plot of the standardized residuals. Okay. So the command to do this in ggplot is you take your model and then you throw it in this function called fortify, okay, which then calculates all of these extra things, and then you're going to plot y as the dot standard residuals. Okay. All right, and so looking at this, we definitely see some kind of pattern in our residuals, so this is a bad sign. And then what do we see? We see these three data points are pretty far out there. Okay, these ones have residuals greater than 2, and then this one also has a residual about 2 units away in the negative. Okay, and this one's almost at 2, but it seems like these three are something quite unusual. Okay, so when we look at the textbook, okay, so looking at the data file, we have no idea what's going on. Okay, but the textbook reveals, oh, these 3 bonds, they are unusual because they're called flower bonds, and they had like certain tax advantages or something which made people want to pay more for them despite the coupon rate being low. Okay, and so they are quite unusual compared to the rest of our data. And so because of that, we would be justified in removing these from our data analysis and saying, let's fit a model that fits the bulk of our data. So we do that, okay? And when we do that, this looks a lot better. We got rid of those 3 lines. This looks pretty good, okay? And we create a plot of the standardized residuals, and this also looks pretty good. We got one residual that's pretty far out here, but it's not too bad. We also see what we consider heteroscedasticity, which we'll have to talk about in a future lecture, which means the variance seems small in the middle but big elsewhere. Okay, so we don't have, it doesn't seem like we have constant variance, but again, the textbook tells us that a lot of these things are based on coupon rates are based on time things, and so that might be expected. Okay, so if we create a confidence model or a confidence interval for the slope. Okay, this is the one with all the data points, and this is for the improved model where we've dropped 3 of those points. Okay, what we notice is that this confidence interval doesn't even contain what seems to be a correct thing. Okay, so looking at this, looking at the confidence interval, it doesn't seem to contain the true slope here, right? So again, this emphasizes the key point that inference based on an invalid model is useless. Okay, so if you didn't try to fix your model and you just said, this is good enough, okay, any inference that you do here is going to be useless. You would have the wrong value for the slope. Your conclusions would be no good. All right, so what do we do when we have outliers? Okay, in the example we just saw, we removed them. Okay, but that's not the best practice for all situations. Okay, you should always look into what these outliers are. If there's a good explanation for them, and if it says, okay, these are atypical from the rest of the data, then you can be justified in removing them. But of course, you want to be transparent with your readers. You want to say, I removed these things from the data because of these reasons, et cetera, et cetera, et cetera. Okay? It could also just be explained with a typographical error, right? Person entering the thing maybe tapped in an extra 0, right? And so, when you're expecting everybody to make donations of about $100, it shows up somebody made a donation of $1,000, and that would show up as something quite unusual or something. So sometimes you can do that. Sometimes you have no explanation, and you just don't know why this point is way out here. We'll talk about whether you should include that point or not. Statistics is all about relating real-world data and making conclusions, and the real world is messy, and so sometimes we don't have good answers for everything. Okay, maybe you need an alternate model. Maybe you need to do transformations to your data. Okay, these are all different things. Okay, so I think the last thing I'm going to get to mention today is Cook's distance. Okay, so Cook's distance is a measure of how much influence a point has in the determining of the regression model. Okay, and what we do is we say, okay, what are the current estimates of y? Okay, and we look at all the estimates. So if you got 10 data points, you're going to look at all 10 predicted values of y along your regression line, and then you remove that data point. Okay, and then so now you have you create the regression line based on the 9 other data points. Okay, and you calculate them for all 10 points, because you can still do that with the regression line. And you say, okay, well, what's the difference between this line where I had the point in and the line where I took that point out and I made it based on the other 9 points? Okay, and so that's the difference between y hat j with I in parentheses, meaning we removed point I, and then y hat j. Okay, and so you do this, you take that difference, you square them up, and you add them all up, and then you divide by twice the estimated variance, and that gives you an idea of Cook's distance. Okay, so this is a complicated formula that we don't, I wouldn't stress too much, because normally we just ask R, hey, what's the Cook's distance on these things? Okay, and it says things like, if a Cook's, these are rules of thumb again. Okay, Cook's distance over 1, that's like a big deal. Okay, and values over 4 divided by n minus 2 are also probably large. Okay, so this is probably going to be something like 0.5 or 0.4, depending on how many data points you have. Okay, and then but every now and then you get Cook's distance of more than 1, and that's something very interesting. Okay, so here's our Bonds model again with the 3 data points, and we can graph Cook's model. Okay, or Cook's distance. Again, using the fortify function on it, we do dot Cook's distance, and we see, this one is like bigger than 1. So this one's really significant, and these ones also have very high Cook's distances. So these 3 points had significant impact on the determination of the regression model. Okay, so Cook's distance is also the book shows the derivation, but it's basically 2 things combined. It's the leverage, so if something has high leverage, it will contribute to Cook's distance, and if it also has a large residual, it will contribute to Cook's distance. So if you have high leverage and a high residual, you're going to have big Cook's distance. But even if you have high of one and small of the other, you might still have a large Cook's distance, depending on how big and how small they are. Okay. All right. We'll stop here, and then I'll talk about the QQ norm next time, I guess on Friday. These are all diagnostic things. So I'm still trying to figure out your homework. On Wednesday, I'm going to go over dplyr. So I want to incorporate that into the homework as well. So just give me a little bit of time on getting the homework up. I'll make sure I give you a fair amount of time to complete it as well. Okay? So we'll stop there for now, and I'll see you guys on Wednesday. I do also have office hours from 5 to 6.